4 months, that's all it took. 4 months after opening, one of the most advanced suspension bridges in the world destroyed itself. Not because of an earthquake, not because of an explosion, not because of a collision. Just the wind. This is the structural autopsy of the Tacoma Narrows Bridge. July 1940. The Tacoma Narrows Bridge opens in Washington State. It stretches across the Tacoma Narrows, a difficult channel of water where wind regularly moves through the landscape. For local residents, the bridge is a major breakthrough. Before it opened, crossing the Narrows meant relying on ferries. The bridge changes that. It makes travel faster. It connects communities. It becomes a symbol of progress. And to engineers, it represents something even bigger, a new generation of suspension bridge design. Longer spans, lighter decks, cleaner lines, less material, more efficiency. The bridge looks modern, but that elegance is part of the problem. Because the same features that make it impressive also make it vulnerable. Almost immediately, drivers notice something unusual. The bridge moves. Not just slightly, enough to feel it. Cars rise and fall as they cross the roadway. Some drivers slow down, some speed up, some avoid the bridge entirely. Others cross it for fun. People begin treating it almost like an amusement ride. The nickname comes quickly, Galloping Gertie. At first, the name feels harmless, a joke, a local curiosity, but the bridge is sending a signal. It is moving far more than a major bridge should, and the movement keeps returning. Engineers know the motion is unusual. They inspect it, they discuss it, they try to reduce it. Cables are added, dampers are considered. Different solutions are explored, but the problem is difficult. The bridge is already built, traffic is already using it, and most importantly, the bridge keeps standing. That matters. Because when something keeps surviving, people begin to trust it, even when it is behaving strangely. Every day the bridge moves and every day it remains in place, the danger becomes easier to dismiss. The motion becomes familiar. The warning begins to feel normal. Then comes November 7th, 1940. A steady wind moves through the Narrows. Around 40 miles per hour, strong enough to notice. Strong enough to shake trees. Strong enough to disturb the water below. But not strong enough to explain what happens next. This is not a hurricane. This is not a once-in-a-century storm. It is an ordinary wind acting on an extraordinary structure. Traffic is light that morning. Workers and observers are nearby. Cameras eventually begin recording. At first, Galloping Gertie behaves as expected. The bridge moves, it rises, it falls, it rolls under the wind. Then the motion changes, and that change is critical. The bridge stops bouncing in the familiar way. It begins twisting. One side of the deck rises, the other side falls. And again. The roadway starts moving like a giant steel ribbon. The motion is no longer uncomfortable, it is violent. Witnesses gather along the shoreline. They are not watching a simple sway. They are watching a structure enter a motion it cannot escape. The deck twists farther. The cables strain. The roadway bends. Concrete cracks. Steel connections are forced beyond their limits. The bridge appears to be fighting itself. But the harder it moves, the worse the motion becomes. Each twist feeds the next. Each cycle adds more stress. Each second brings the structure closer to failure. Then pieces begin breaking away. Sections of roadway collapse. The center span starts to tear apart. And finally, hundreds of meters of steel and concrete fall into Puget Sound. A bridge built to last for decades is gone in months. Remarkably, no human lives were lost. But the collapse leaves engineers with a disturbing question. How could ordinary wind destroy a major suspension bridge? At first, the answer seems obvious. The wind must have been too strong. But the evidence does not support that. The wind speed was well within what the bridge was expected to survive. So investigators look elsewhere. They examine photographs. They review construction drawings. They study the film footage. They inspect what remains. They look for overloaded members. They look for weak materials. They look for a hidden construction defect. But the usual explanations do not fully fit. Nothing simply snapped without warning. Nothing struck the bridge. No single overloaded truck caused it. No earthquake shook it loose. The failure is stranger than that. The bridge did not just break, it entered a self-reinforcing motion. To understand the failure, look at the deck. The Tacoma Narrows Bridge had a narrow, shallow roadway. That made it lighter, it made it cheaper, it made it elegant. But it also reduced stiffness, especially torsional stiffness. In simple terms, the bridge could twist more easily than it should have. And once it started twisting, the wind did not just push against it. The wind began interacting with it. As one edge of the deck rose, the airflow changed. As the other edge fell, the airflow changed again. Instead of calming the motion, the air helped drive it. Like pushing a swing at exactly the right moment, each cycle added energy. The bridge was not being overwhelmed by wind, it was amplifying it. Ordinary wind became extraordinary motion. and the structure had no way to bleed that energy off fast enough. That is what made the collapse so important. It proved that wind was not just a load. Wind could become part of a dynamic system. The bridge and the air were interacting together, and the design allowed that interaction to grow until failure became unavoidable. This changed bridge engineering. Before Tacoma Narrows, engineers understood that wind mattered. But the collapse showed that wind could not be treated as a simple sideways pressure. It had to be studied as movement, as airflow, as vibration, as interaction. After the disaster, bridge designers began paying much closer attention to aerodynamic behavior. Wind tunnel testing became a standard part of major bridge design. Deck shapes changed. Stiffness requirements changed. Engineers began designing bridges not only to carry weight, but to control motion. Modern long-span bridges carry that lesson forward. Every wind tunnel model, every test of how a bridge behaves in moving air owes something to Galloping Gertie. The bridge failed, but the failure taught engineers how to build better. The collapse occurred during ordinary wind conditions. The structure was not destroyed by extreme weather. It failed because its design allowed wind-driven motion to amplify until the bridge could no longer absorb the forces acting on it. Sometimes structures do not fail because nature is stronger. Sometimes they fail because a design unknowingly magnifies the forces acting upon it. The Tacoma Narrows Bridge did not simply fall, it revealed a new kind of failure. And that is exactly why engineers still study it today.